this computer. Hi all, and welcome to the Medical AI Lab talk series. I'm delighted that today we have Shreya Shankar present challenges in real-time ML monitoring. Currently, Shreya is doing their PhD in databases at UC Berkeley, building systems to operationalize machine learning workflows with a focus on end-to-end observability for machine learning systems. So without further ado, delighted to have you here, Shreya. Take it away.
Well, thanks for having me, Pranav. Let me share my screen. I hope that you'll be able to see it. Do you see something? Yeah, okay. And then if I press play, do you also see it bigger? Lovely. Okay, awesome. Great. So thanks for having me. I'm super excited to be here and talk about monitoring streaming ML with feedback delays. I'll get into that a little bit. This is 30 minutes, I'm assuming, so we have a few minutes for Q&A at the end. But feel free to interrupt me at any given point with any questions. Happy to answer them. So I'll talk a little bit about kind of why dealing with ML pipelines sucks, which many of you are probably familiar with, especially if you're trying to work on applied ML. Recap a little bit of like, what is data set shift? What does that even mean? How do we think about it in a practical context? I'll introduce a toy ML task that will illustrate kind of the challenges I'm talking about. And then I will follow up with some of like the challenges in monitoring. Why are we monitoring? How do you get or sustain high performance in your pipelines? And a little bit of background on myself. I guess I should have started with that. I did my undergrad in CS, also at Stanford, like many of you, undergrad in coterm. I worked at an applied ML startup for a couple of years, and now I'm a PhD student in databases at UC Berkeley. So very exciting trajectory and exciting to share more of the problems with you. So starting off, right, dealing with ML pipelines sucks. And this is a very industry-focused perspective. When you're in an organization, you have several different components in your ML pipelines. So here you could have something pretty straightforward with just one model. You have some ETL, extract, transform, load components, which takes your raw data, generates features from it. You want to split that into some train and val sets, pre-process that data, train models, fit a calibrator, whatever you want to do, put it in some sort of model registry, and then serve that online or serve some predictions online made from it. And at every step or component in this pipeline, there's like truly like 100 tools you could choose from. That makes production ML just such a pain to deal with. And so many things can go wrong at any step of the pipeline or any component of the pipeline. Oh, resume share. My screen sharing is paused. What happened? Okay. Yeah, so many things can go wrong post-deployment, making it really hard to trace these bugs. So for example, you could have corrupted upstream data. Maybe somebody who developed the model is now on leave. Maybe somebody made assumptions in train time that don't quite hold in practice. And then of course, data is drifting or changing in nature over time, and maybe we have to retrain our models. So there's a lot of stuff that can happen. It makes debugging a huge nightmare. So how do we even think about solving this? How do we think about enabling practitioners or people who are working with these applied ML pipelines to keep high performance? And from a data management perspective, observability is kind of a catch-all term to instrument your pipelines with some logging or some metadata so that after bugs occur, you can really easily query for where they happened, why they happened, and how you can fix them. And the idea here is you can't really catch all the bugs before you deploy your model. But once you find a bug, you want to minimize downtime of the system. So when we're building these kinds of observability tools, we want to, one, help people detect bugs, and then to help people diagnose bugs. And specifically in the ML context, right, there's a wide variety of skill sets, practitioners, data scientists, data engineers, domain experts. All of these people work with the predictions and need to be able to debug them. So how do you build a tool that generalizes to them? There are three kinds of broad classes of data management for ML solutions in the database world, I think. So one is around kind of what do I need to start training a model? Give me like all of the features in one place, version all of the data. Another one is in experiment tracking. Many of you might use this. Weights and biases, ML flow, and whatnot. And then finally, like the observability solutions, which is more unexplored. But how do I kind of find bugs in my, how do I know when my ML models are underperforming, especially in the absence of labels in real time? And that's mainly what I'm going to talk about today. So, okay, the software industry kind of has like this rich history of monitoring, and it's not that hard. You kind of just know exactly what you want to monitor, maybe like latency of your requests, and then you just log those values and then query them in a dashboard somewhere. But for ML, right, it's like slightly harder because we're tracking a lot more things. We don't quite have all the information we don't have labels, for example. We still want to do real-time ML performance. And then of course, right, like data is shifting over time. So to be more concrete about this like lack of labels, many times, I'm sure, especially in like medical settings, when you're deploying your model, you don't have labels, or you deploy them in new hospitals, or you deploy them in new, subpopulations, but you want to know how well you're doing in these areas without getting like humans to manually label and annotate them. The other thing that is true for like temporally evolving data is that you might get performance drops, but sometimes there's temporary or like seasonal, and maybe that's expected. So maybe, for example, I have a model that performs worse on weekends than weekdays. Totally the case in a lot of these like ride sharing startups, for example. And then finally, you have some sort of degenerate feedback loops, which is like practitioners or people are actually doing something with my model outputs, and that changes how my model behaves somehow. So how do I monitor this performance? Maybe recommender systems is a really good example. So I'll talk a little bit about shift before I go on into the monitoring with label delays. So I think there's like a lot of blog posts and like papers out there that define a bunch of data shifts. And a lot of them are kind of the same thing, and it can be hard to reason about. And so there's two questions here, like what are the shifts that we care about that require models to be retrained? And then two, what does it even mean to attach labels to the shift? Like, do I really care if this shift is defined as like covariate shift or concept shift? Do I care about identifying one or the other? These are all great questions. I don't think people have fully explored them, but from my perspective, I care about the kind of shift as a way to figure out how to retrain my model, and I'll get into that a little bit. So first off, just to give you an example, suppose X is your feature or covariate space, and then Y is your label space. So you have your feature distribution, P of X, you have your label distribution, P of Y, and then P of Y given X is the distribution of labels given specific features. And this is what our ML model is trying to learn, right? Like we want our model to take in some X and then predict the Y for it. And it's really hard to know whether there's a shift in P of Y given X. And that's like the whole challenge that we have here. And the community has kind of assigned a lot of terminology to these kinds of shifts. So for example, covariate shift is P of Y given X is the same, but P of X's changes. And I've heard like subpopulation shift for this, a lot of data shift. I don't really know all of the terms out there. And then there's a concept shift, which is P of Y given X is changing, but P of X is the same. And then I've also heard this is like, gosh, what is it called? No, predictive power drift or something. I don't even know. But there's a ton of terms for that. And then there's also like label shift and whatnot. But the point is here, like these are kind of the two shifts that really occur. And any other shift is encompassed by Bayes' rule. If one value here goes up, the other one goes down somewhere. And in practice, right, both of these are going to happen repeatedly. Like you're going to have some form of covariate shift as well as some form of concept shift. And your challenge is kind of like when what do I need to know? Like, when do I actually retrain my model? And then if there's more concept shift than covariate shift, maybe I only retrain my model on a recent window of data. But if there's more covariate shift than concept shift, maybe I have underrepresented populations in my data, and then I need to think more critically about like what am I going to augment in my training set? How do I do that? And those are the implications. I see some blank faces. How are people feeling right now? Make sense so far? Okay. I will keep going. And then you have these shifts in the wild, and there's a lot of ways that people are trying to track them, again, with the purpose of determining when to retrain their models. And I think at least I've seen like a few levels of sophistication out there. One strawman approach is I'm going to track means and quantiles of all of my features in my outputs. And then I'm going to alert if one of these values is like anomalous. Okay, cool, but this kind of goes out the window if I have like thousands of features. What am I going to do if like one feature's mean changed very slightly? And then there's like a layer on top of that, the I took a stats class approach, which is somebody's taught me what distance metrics exist out in the world. So there's like MMD, mean discrepancy, like the Kolmogorov-Smirnov test, chi-square test, I don't know, like whatever statistical test you want to run to determine whether two distributions of data are significantly different. But you do have problems from here around like, if I just have a large number of data points in my samples, I will have low p-values come out of these test statistics just by this large number. So I want some method for telling me when there's shift that's higher precision, so I don't get all these like crazy alerts that are telling me to retrain my models. So how do we do better, right? And one idea here, right, is like all of the approaches right now to monitor like your ML pipelines post-deployment are label unaware. They don't use all the information that we have, right? Like we sometimes can get a few labels, a few annotated examples, and think about, okay, is our performance doing as we expect? So can we do better, right? Like how do we do better? Again, the goal is to be able to increase precision on the alerts on when to retrain models. Cool. So to illustrate some of these challenges, I will give you guys a toy ML task. So on the New York City taxi cab data, where every row is a ride, basically a taxi ride in New York City, we want to predict whether a taxi rider is going to give their driver at least 10% of a tip. Reasonable tip is in quotes because I think this is different based on different locations. And we use data that's publicly available online. We have this like random forest classifier that we train, and we store the data in data frames. And the goal here is to evaluate accuracy over time. And we have a pipeline. I will skip this. It's not as necessary. But we have a pipeline here, kind of with like cleaning, feature generation, training. And as you can see, some of the components are shared between the training and inference pipelines. And the tables here, let me explain that, show you kind of like, what does it even mean to have like label delays and label lag or feedback lag. So maybe inference like generates 3 different predictions at 3 different timestamps. And your feedback, or like in our case, like the taxi meter payment data or the credit card company payment data comes in at a later date. For each ID, we get some true value or some true label, and that comes in at a different timestamp. So at any given point in time, right, we have either no feedback, we have partial feedback, or we have full feedback. And the challenge here, right, is like you do a join between the two tables or between the inference and feedback components. But how do we know, right, if that's like t equals 1 and t equals 2 case, that like, how do we even know how we're doing? How do we know in a partial feedback case, how are we doing? 100% is very different from 60. These are just toy numbers, just to illustrate kind of what's going on. So at every given point in time, right, can we develop like high accuracy methods to estimate the performance? Cool. And I'll skip this because this slide I gave to, this is a more academic audience. But anyways, at a high level, covariate shift, an example of that is you have more taxi rides in like a certain area in New York, and concept shift is maybe like heavy construction in certain areas causes these rides to take longer and people actually tip less. But that's like a more complicated thing that shows up somehow in our accuracy. Cool. So now the meat of this kind of talk. So the challenges, and we have these label delays. How do we, with high accuracy, estimate that accuracy? And so I break it up into two kind of classes, which is coarse grain monitoring and fine grain monitoring. And I don't know where that slide is. I think I accidentally skipped it. But the idea here is coarse grain monitoring is monitoring like estimating accuracy when you don't have the labels. And then fine grain monitoring is explaining why our estimations are decreasing so that we can like augment the training sets somehow. So in the detection problem, right, there are three cases, as I mentioned before: full feedback, partial feedback, and no feedback. So in the full feedback case, what are the challenges here, right? Like you have all your predictions, you have all your labels. All you need to do is like simply do a join, right? Do a streaming join on predictions and feedback and compute your accuracy on the result. Doesn't sound hard, but what if the data is too large to fit in memory? And maybe this is not the case in ML or medical applications, but it happens a lot. And like I was talking to someone at Facebook and they just subsample their data and joined that, which is okay. Yeah, fine. We can do some sort of approximate streaming join. We subsample our streams before the joins, but if you uniformly do that, uniformly subsample the streams, you get quadratically fewer resulting tuples. So I can explain that a little bit more if people have a question. But the challenge here is we want to subsample our streams in some sort of stratified approach. And the question then becomes like, how do you construct the strata, right? Like, what are the subgroups that you want to sample from in your inference and your prediction, or sorry, in your inference and your feedback streams. Again, randomly subsampling your streams yields quadratically fewer samples. We want more, we want our we want our approximate accuracy to be as close to the true accuracy as possible. So the ML idea here is, okay, like I want to bucket my data in these streams, and I want each bucket to have similar prediction errors or losses such that I can just sample from these buckets and then compute the join, compute the accuracy on that. And then I can feel more confident that my estimated accuracy is as close to the actual accuracy. So in this case, right, the research challenge here is how do you create these like evolving buckets over time with similar predictions errors or similar losses, especially when this data is changing, right? Like one naive example is let's train a decision tree to predict loss and then use the leaves as these clusters. A more data management approach is to use some sort of streaming algorithm like frequent item set to come up with loss clusters. But the problem with these approaches, at least from like preliminary work, is there's a lot of hyperparameters you need to decide here. It's very focused on tabular data, really unclear how to do this in image data. And you need to constantly be retraining these bucket models, right? Like what's going on. So unfortunate, we're still thinking about it. If people have ideas, please let me know. Cool. So moving on to the no feedback case, which is this one is way more common, I think, in practical deployments. So the problem here, right, you have no labels at all, but you still want to know what your performance is or estimate your performance. And so a naive solution is to importance weight your accuracy. And I'll give an example of that. So you split your train set into some sort of buckets and you compute the accuracy for each bucket. And then at inference time, you take each data point that you see and then assign it to one of the buckets that you created at training time. And then based on the representation in these buckets in the inference data set, you importance weight is the term, but you kind of multiply the representation by the training accuracy, add them all up, and then that's your estimated inference accuracy. So for a concrete example, suppose I have like locations FIDI and Midtown. In the training set, they had accuracies of 80% and 50%. Once I've deployed the model, maybe I see 100 FIDI rides and 500 Midtown rides. So I do the math to estimate the final accuracy to be around 55%. And these are just completely made up numbers. So don't read into it too much. Just an example out there. So, okay, this is cool. Like we've been thinking about importance weighting for how many years now? Like it's not new. But what happens when your bucket representation changes drastically? So for example, here, suppose I trained a model on January 2020 data, and then I'm running inference on, I don't know, some week after I've deployed it on February 1st. I can't see my cursor, so I don't really know what the week is on the second chart here, but over time, right, the bucket representation can change, and this can impact how confident we are in, or basically, yeah, like with this covariate shift, right, like how accurate are our results going to be? Super open question. So, I don't know if I can advance slides. And yeah, to show a graph, right, like just using this naive location bucketing strategy, the blue line is the estimated accuracy based on the subgroup representation. And the orange line is the actual accuracy that happens. So clear, and this is a crazy example because COVID happened right here in the middle of it. But you can see a huge divergence, right, between the estimated accuracy and the real accuracy. And then it does get smaller over time. And so what does this mean, right? Like if we were predicting this blue line, we would see a drop, but it wouldn't be as large as the drop observed in the real accuracy. I don't know. So maybe that implies concept shift. Maybe when it's closer together, the estimated and the real accuracy are the same, but the accuracy goes down. That's some sort of covariate drift. Again, right, this even generating this plot requires the labels. So the takeaway that I want to give here on a plot like this is, I think it's, what are the kinds of like metrics that we want to track, right? Like maybe when we get labels, like we want to track like a divergence between importance weighted estimates and the actual accuracy. And that can tell us kind of what we have concept shift. Maybe do we want to retrain our models? Maybe unclear. But the other underlying question is, what if our bucketing strategy is bad? Like it's just not good. And as a result, we have a huge divergence in the estimated and real accuracy. So for example, maybe I only have 2 buckets in the data, right? Like then the estimation will just be terrible if the data drifts, right? So what is like the number of buckets we want to have? What is the strategy we want to have? Maybe pick up location. I just pulled that out of thin air. Maybe that's not the best strategy. But again, like open questions here. So again, yeah, how do we construct the buckets? Goal here is we want to have the most overall approximate accuracy in some way. And a challenge is we want our buckets to have good representation in training and inference sets. So for example, if I just run clustering on the inference data, there's no guarantee that those clusters are going to have good representation in the train set. If they have like only 2 or 3 examples in the training set, like how much can we trust the accuracy in that bucket, right? We need some number of points in each bucket. How do we create the buckets with substantial representation in the training set? Maybe we do some clustering, like weighted combinations of training and inference set. Maybe we do some sort of hierarchical aggregate summaries. So that's like, again, like training some trees or partitioning the data in a way that like has representation of both training and inference sets. again, right, like lots of hyperparameters to decide. Constantly, we need to be recomputing these buckets, right? If I train a tree, it's really hard to do that in a streaming setting. When do I decide to recompute my buckets? I don't know. So fortunately, I have no great ideas there, but if you have an idea for your buckets for your deployment task, right, like that's probably helpful. Naive importance weighting could work pretty well. Cool. And then finally, I'll talk a little bit about the partial feedback case, which, yeah, sure, maybe you can simply aggregate the full feedback and no feedback cases. But another interesting side challenge here is the feedback delays might be different based on different groups in your data. So some data points might have longer feedback delays than others. And these delays might not be uniformly distributed. So for a concrete example, suppose there's a power outage in a neighborhood in New York City. And as a result, like randomly, we're not getting labels for like one location. And we didn't expect that to happen, right? Like the reality is like you're going to have upstream engineering issues somehow that make it such that your delays aren't uniformly distributed. So for a debugging purpose, right, in the vein of observability, we want practitioners to know when things are going wrong. How can we kind of identify groups of similar data points with similar feedback delays, present this to people and say like, oh, by the way, you're getting new feedback delayed point, or you're getting more delays in the Midtown area, or you're getting more delays in this group of data points, and this is changing in this way. So maybe you should go fix the broken sensors that are in this subpopulation. I don't know, just make that up, right? So again, how do you identify groups of data points with similar feedback delays and track that over time? Cool. So what is my computer is passing. So that's kind of the overall view of coarse grain monitoring when you don't have the labels. What are some strategies? What are some research problems in thinking about estimating accuracy as accurately as possible? And then a little bit about fine grain monitoring for 5 minutes or so. Once I know my coarse grain accuracy is dropping, right? Like, why is it dropping? What features are underperforming? How do I augment my training sets, right? Like this is the diagnosis part. That one was the detection part. And a key challenge here is we've got to be able to separate like engineering and data quality issues from actual data drift issues. And how do we do that? So the standard way, kind of an industry, is you have a bunch of data quality checks in your pipeline. So you alert on missing data, set upper and lower bounds for each of your feature values. But this is really annoying to scale to thousands of features. Maybe these upper and lower bounds evolve over time, especially for features like age that become like cumulative in some way. So you have to have some sort of data engineer manning that at all times. And as a result, I've seen a lot of like practitioners push this kind of data quality verification onto shift detection because, yeah, I mean, like if your mean feature value drops a lot, like, or if your KS test statistic is super high, yeah, maybe like you'll flag this data quality problem in there, right? But you do want to be able to tease out broken sensor from this feature is actually shifting and we need to, I don't know, change our training set in some way. So if you think about like towards retraining models automatically, as I mentioned before, right, using the methods to compute shift doesn't work well in practice, especially when you have like or you have at least like a few thousand data points. You're going to have low p-values. You're going to have alert fatigue when you're monitoring every feature in every output column, seasonal expected shifts. So one naive idea here is when we know our coarse-grained approximate metric is low, why don't we look at these KS test values or what columns are most anomalous, again, to reduce that alert fatigue. And cool. So when we do that, different shifts, right, imply different retraining strategies. Like for example, for covariate shift, maybe I want to upsample some of the buckets in training because now they're more represented in inference. Maybe for concept shift, I want to retrain on a recent window. Maybe I want to use a different model. Maybe there's like a new drug that came out that's like fundamentally affected P of Y given X. Maybe that, I don't know, like fewer people die of this disease. So this becomes like a class imbalance, more of a class imbalance problem. I don't know, like these kinds of things actually require a lot more of like data science work in the back end, right? So how do you, with all of this, right? Like how do you create these training sets that adapt to the changing nature of the problem over time, right? Open question, we're working on that. Have unfortunately nothing to say more about it. Cool, so that leads into the final kind of minute or so of stuff that I'm working on with ML Trace, which is our open source like bolt-on ML observability tool. The idea here is you add decorators to existing components in your pipelines, and we can kind of monitor things and log relevant data for you to query to solve the kinds of problems outlined earlier in this talk. So we are working on data systems, machine learning, and HCI projects. The ones that I'm really excited about are listed here. So I won't read all of the words here, but if anyone's interested in kind of these project areas, we're definitely would love to talk to you. Please email me or reach out. Yeah, and I will leave you with several words that I have written, which you can read on your own time if you're interested. But also if you want to email me, please feel free to. And yeah, thanks for having me.
Thanks a lot, Shreya. That was great.